It is my honor and pleasure to introduce Professor Samuel Sánchez. We're just talking now that if I have to mention every award that he's had, we're going to be here for a while. He's a very accomplished professor and scientist. He's an ICRIA professor and the deputy director for the IBEC, the Institute of Engineering of Catalonia. And he's received, just briefly mention some of the awards, he was on the Top Innovator Under 35 in 2014 by MIT. He received the Princess of Girona Scientific Award in 2015, the National Research Award for Young Talent in 2016, Scientific Excellence Award from 2022 from the Spanish Royal Society of Chemistry, the Banc Sabadell Foundation Award for Basic Science and Engineering Award, and the Constantes y Vitales Award to the Young Talent in Biomedicine. He is also an elected member of the Young Academy of Spain, and in addition to all his research, right? So he's been very successful in his entrepreneurship side, right? As he's the CSO and the CEO interim of a spin-off of nanobots therapeutics cell. So he's been an inspiration for all the nanorobotics community. So please let's welcome him to the stage.
Thank you. Thanks, Abdon, for a nice and very kind introduction. Thanks to the organizers and also you and Danny for inviting me. It's a pleasure to be here, and more particularly in the round table where I have two dear colleagues who were also joining me in this nano adventure a few years ago, and now they have their own successful career, and I'm happy that they will be presenting after me. So again, welcome to the nano world, but based on the things that I've been hearing these days, I also added a little bit more. As you can see, I changed my title, not only nanobots, but also 3D biobots, and Maria will be talking about that a little bit in a while. So we hear this morning about 3D bioprinting and smart materials, so at the end of my talk, I will be going more, shifting from nano to the micro world. But I have a few keywords here and a few pictures, so again, you will hear a lot, and this is also put here like bio-inspired robots, right? Inspiration by nature, things that are swimming around, but at these very small scales, but we are mimicking the micro and artificial life. But hybrid robotics is something that we kind of made up this name, but just for you to have an idea of what you'll be hearing today is the combination of biological and artificial components. So I think most of the talks during the last 1.5 days were mainly about artificial materials, right? So how to make submarines, how to make robots, different scales, but what if you combine with single-cell multicellular systems or enzymes or molecular machines? So this is what you will be hearing today throughout my talk. But going back in time, so this will be actually my outline. So I don't have bullet points, I just have pictures. So inspired mainly maybe by these books and these movies as well, like how to make a nano submarine, and the question here, or how to make compliant and soft robotics that are not as rigid as they used to be. But the question, and I hope we can answer this at the end of my talk, how far are our robots from science fiction? So first I will go again into the nanoswimmers and things that are nature-inspired at the nanoscale again. So we're getting motion at that scale is extremely difficult. And having things that are moving not at single particle level, but having collective motion like we see also in life, this is extremely beautiful, fascinating, but extremely challenging. So making something nano is a challenge. Making something nano that moves is extremely difficult, right? But then if you want these things to make something sense, clean, deliver drugs, or anything else, you need billions of them, right? And then Maria was asking actually today also like to some of the speakers, what actually do have done, what did they swarm? Do they really behave like intelligent systems or not? Or do they just aggregate, or do they collapse? But today we're not talking about that. We're talking about things that go under the water, right? So this is mostly our inspiration, and that's what we want to mimic. So I want you to look at this video a little bit, and and the previous video, some similarities, these convecting flows, right, this spontaneous migration, they don't collapse, right? They feel like attack or not, right? And then when I look to the reality of our lab, actually there was like from Anna Ortela a few years ago, she showed me this video, and I say, oh my God, this is actually what we just saw. But these are the nanoscale. So what you're seeing here are thousands or millions of nanobots, like nanoparticles that self-propel in a liquid. They're actually underwater, right? They're moving in 3D. They aggregate at some points, but they form these convecting flows, right? They can be moving by through hours and hours and hours. Okay, so probably we could finish the talk here because you have seen the end of my talk, okay? But now I want to tell you how do we get here. And I told you that it's very difficult. So why is it very difficult to make things moving at the nanoscale? So in the 1977 Purcell talk about these things like what happens when you shrink a swimmer, right? If you go down, and everyone in the room should know about this, right? More than me, because I'm chemist, not a physicist, or engineer. So you might hear about Reynolds numbers. So you go down. So we are 10 to the 4, but the physics that you saw in the previous video is 100, and you go down to microswimmers, it is 10 to minus 4. So what does it mean? It means that inertia is negligible. So viscosity is extremely higher. So what he said, as you may know, right, is like if that will be making something moves at nanoscale, is like moving a pool full of honey. So what we need is make things that are continuously propelled. So if you stop the propulsion, you don't go anywhere. Actually, they talk about the micro, like the bacteria, they will move 20 nanometers and stop propelling. So making this propulsion, continuous propulsion is one challenge. Second one is it has to be strong enough, right, to overcome the viscosity. Okay, so how are we going to build these nanobots? So we need at least 2 components. Like all the smart people in the room can add many other functionalities, right? But we are very simple and simplistic, so we need at least 2. One is a particle, the chassis, and the other one is the engine, right? I mean, this is very, very obvious if you think that things need to be moving. So how do we select the chassis? So again, looking into nature. So you look into all these different chassis, different structures, cancer cell bacteria, and that's exactly what we reproduce in the lab. We make microparticles, tubes, elongated rods, or nanoparticles similar to a bacteria. And in our case, we want to use them for biomedical applications. So one of the main key points here, talking about material, has to be FDA or EMA approved. But you want to also, you can make smart materials, you can make polymeric, biodegradable, and we hear also today about 4D materials or smart that can be responsible. Second component is engine. Okay, so we use catalysis because I'm a chemist and I like chemistry. Catherine likes light, so she's using light, so you will see her talk later. We have here also Dani and Abdon, magnetic control, magnetic actuation, and other people use acoustic waves. So again, inspired by nature, nature has done this. So if it's so challenging, how do they do it? So converting energy into motion through chemical reaction, chemistry using enzymes, by the way. Now the first thing, before I keep talking, because I'm talking really a lot here too fast, now I give you one moment to look at this video. I told you, like probably 7 times so far, nature inspired. Right? Copying nature. So now you are seeing one video is a bacteria, one video is an artificial bot. And now the question for everyone to wake up, and whoever is at home watching this video, who thinks that, I don't know, Abdon, what do you think? We start, and then who is following you? Which one you think is a bacteria, which one you think is an artificial robot. So here, my challenge to you, right, is to make here a statement like voting. And the point will be trying to bring you some hesitation here, so to convince you that they're pretty similar. Adon?
I don't know. I said maybe this one is the bacteria.
Who thinks the same as Abdon? Okay. Who thinks the other one is a bacteria? Oh, yeah. Okay. So this one is a nanobot that you can find a Guinness World Record. So this is the smallest jet engine. So yes, we make turbines also. We also make jets. Here, this is a nanorod coated with an enzyme that in a solution, right, or the fuel, they will self-propel. And yeah, this is not a joke. You can find this in the Guinness Record. Okay, good. Okay. So if I go back in time, we're doing jets before. So when I moved from Japan to Dresden, then to the Leibniz Institute, we're making tubes, and these tubes have a platinum inside. Platinum catalyzes the composition of peroxide into oxygen and water. Oxygen accumulates into a bubble. Bubble are expelled through the larger opening, propelling, like a propeller. Okay. With this, as you can see, we made, these are some of the publications, but we could not go very far into medicine, right? But we opened a new field, which was cleaning water. So because this can be making chemical reaction, like the Fenton reaction on the outside, and then you can clean pollutants. You can see we want to use bubbles because bubble will be mixing the fluid, and I'm going to go, because this is not the topic of my talk, Anthony will talk about environmental applications, but just to tell you that big and larger robots making bubbles, then they can make chemical reactions for cleaning, or also with graphene coating, so trapping contaminants like heavy metal we did here. And you can put this, of course, deploying into the ocean. I'm sorry, maybe it's too small for that. You can think about different designs, but deploying into a microfluidic device where you want to clean or accumulate the contaminant or your analyte, as we did here, is what we were doing. So Maria actually had an idea a few years ago. Instead of deploying there, what if we put this into a sponge? And we deploy the sponge, right, into the solution. So this is what we're doing. And actually, you can reuse the sponge many times. Or if you put magnetic materials, you can control by magnetic field this boat full of water cleaning particles. Okay, so then we try to go down in size. And I don't have talked today about Janus particles. So Janus is the god of the two faces. So now instead of putting the catalytic material in the inside, we put it only on the one side, on the black side here, and it makes the same chemical reaction. It will generate a chemical gradient or a fluid gradient, and then pushing the particle forward. And in this case, luckily for us, we can shrink from micron down to the nano side. Now, what about the engine again? Okay, so we want, and I'm sorry, I will be going now into the bio life, right? We want to make everything fully biocompatible, so we use enzymes for this reaction because you have thousands of enzymes in your body. So what is the best propeller? Actually, we have a patent now where, like in the US, they're asking us, like, what is the enzyme? Is the enzyme a propeller or not? So, well, if it propels the particle, then it would be. So what is the best propeller for our robots? So what we did is to compare 4 different enzymes. Sorry because going too much into the chemistry, but this is the only plot I will put in here. So it's very trivial solution, but it's the faster the catalytic turnover, the faster the chemical gradient, the faster the fluid flow, the faster the propulsion. Okay. So the best enzyme happened to be, in our case, urease. And now the second point is, if you have to design your robot, your propeller, your ship, let's say, where are you going to put the enzymes? Are you going to? We don't want to make Janus. We can make it very simple. So we cannot put them inside because then you need to make holes. So what if we make it bad? Let's make it bad, the distribution. So that's the best solution. So if you have them making patches, totally asymmetric, you will generate vector force, and we check this by super resolution microscopy, and this is actually the answer, right? If you have something which is fully coated, won't move anywhere because the forces will balance. If you have no fuel there, they will not move, but this is our microbot. Okay. Hey, we can check this by micro nanoscale. This is not big issue here. And you can do this for any type of particle, okay? The ones that I showed you before, from the nano, all the size, to the micro, and so on. This, okay. What else? We want them to be multifunctional. So some of the challenges here about sensing, right? You can transport, you can sense, you can act, you can target locations. Again, in the bio world, right? So we demonstrated by having these nanobot moving drugs, they will internalize and enhance the drug delivery into cancer cells. We also showed that by using DNA switches, they can open and close and detect the pH, which is around. You can also have molecular gates, so only when it's inside a cancer cell with a low pH, a 4.55, then they will open the gate and release the cargo. And also we wanted to target spheroids of bladder cancer in particular, because remember I told you the best enzyme was urease. Urease takes the urea fuel, urea is in the urine is in the bladder. So in this case, we use antibodies to target specifically, because what we want to do is precision medicine going inside the tumor. But again, we need millions of them, right? So we want to, again, use this intelligence that happens in nature. And going again into nature, we just 2 weeks ago, we we published the beginning of the understanding. So why they move like this video in 3D. So what we did again is to look into nature. So on the left side, so what you are seeing is bacteria that needs to take the oxygen from the surface. So this is totally bio-inspired. On the left side, again, is a bath, like very dense bacteria. They are going up, they are scattering, taking the oxygen, and then going down, making these plumes, and then going up again by buoyancy, up and down. So this is actually what happens to our system. If you add a drop of the swarm of nanobots, the products will be lighter than the substrate, then we'll make the whole ensemble to go up, scatter. As you see, these are the simulations, right, that we run with Igor Aronson from Penn State. These are our experiments looking from the side. A drop goes up, scatters, and goes down. The density is not as high as the other one, but this bioconvection that happens in nature is actually one of the key components in our swarming behavior here. And again, that's what I said, we just published two weeks ago in Nature.com. Okay, yeah, again, bladder, urine, we have all the components there. So we wanted to put inside this underwater, under urine, actually, we can say it, right, in the bladder. And we were the first ones to see this collective motion happening, but using medical imaging techniques. So that's what we report here. By the way, this also helps the fluid mixing. So you want them to be collectively moving. And the reason is because, again, I always use, the other day, I just, in Maria's conference, it dropped down the whole water. So anyway, yeah, this will drop down. So if you are a patient, right, they will ask you to lay down like this, and the liquid will sediment and touch only one side of the bladder, but they will ask you to rotate every half an hour. Okay, I can tell you because my aunt goes there like every few months to make this treatment, and it's a big pain. So if you could accelerate and have a fluid mix in there where all the drugs will mix together, it will be more efficient. So that's what we are doing. So just to see the comparison, so particles on the left side are passive, they just sediment. If you add the fuel, they will go in 3D. So here we radio label them in microfluidic chips to see that in the presence of urea, they will go much faster than if there's no urea. Again, we look into that, and that bladder of the mice that we have emptied. We emptied the bladder before. You inject the nanobots. The nanobots is this red cloud that only when all the components are there, they are moving, touching the whole wall, as you see here in the CT. So what else can we do with this? So of course, we need to generate the tumor and treat them. So we have a consortium here, and paid by La Caixa Foundation. And yeah, we have all the components with the clinician expert or on bladder cancer and imaging people. And we just published this in April in the cover of Nature Nanotech. And what you're seeing here is not AI generated. It is actually the ex vivo bladder that we took, and by light sheet microscopy, I will show you in a while. So we can make sections of it. We can see the tumor on the left side, and these red, yellow colors are the nanobots which have been accumulating, and that's what we want to demonstrate the treatment of bladder cancer. Okay, so this is again, you see, it looks like a jellyfish motion, so it's like really collective moving in 3D, and that when we put into the mice, in the bladder of a mice, you can see here the control. You can see by MRI how the tumor is growing, like we have injected into the bladder with the tumor different controls, and there are no significant differences if they don't move. But once we have self-propelled nanobots, they will accumulate high concentration, high signal by PET-CT quantification on the right side. But that was not enough. So we wanted to see whether we can go not only to the outer surface of the tumor, but inside. Because the drugs already stay on the outer surface. That is the problem, right? That many, like they said, less than 1% they get to the tumor. So that is the light sheet microscopy I was telling you. So we have the bladder. You can see the video going up and down, in and out. So you can see the healthy urotelium, like very smooth. On the left side, like in diagram, on the left side, you can see the tumor. And again, the exact correlation by the scatter signal from the nanobots that not only stay there, but they can go all the way to the lumen of the bladder. You can see here the correlation of the side. And you can run the AI now, but just to quantify that less than 5% stay in the healthy wall, but 95% stay on there. So we use iodine to treat the tumor, and just very shortly, I will show you, this is a summary of the whole paper, very quickly. Normally people go between 6 and 14 times to a hospital to be treated by the therapy, which is right now typically BCG or mitomycin drugs. So in our case, with only one administration, we stop the tumor progression, or if we increase it, we could reduce to 90%. And this high and low concentration, actually, very quickly, it's the same concentration that you use in clinical trials, okay? And this is just a summary. So we're about those numbers, and the free radio labeling does nothing. So they need a swimmer to bring the drug to the location. Okay. So we have a very versatile technology. It's not only the swimmers are not good only for that. They can cross mucus. They can go through the ocular vitreous. They can go into the joints, and they can also treat antibacterial biofilms. So again, we have a few publications in that direction, but I'm not going to go into that. Katerina and also Abdon have covered that, but we can play with this. And a bit of publicity and also disclosure of conflict of interest. Of course, like this, I'm CEO and CEO interim. CSO and CEO interim, and we are opening in 3 days. Now it's updated to 97%. So while we are here, people are investing. Yeah, if you are interested, you can check that, because it's going very quickly. So we are happy with that. Okay. The second part is going larger now. Again, how can we now change gears? So nothing is going to be at the nanoscale, but things will eventually be moving. They will be swimming. I told you about, again, hybrid robotics, and now why and what for. So in our case, now I will tell you about the larger scale, right? Now we are going down in this hemisphere, so we're going to have multicellular systems with hydrogels. And hopefully we can incorporate some robotic systems like sensors and electronics. So we can use them for in vitro muscle model. So people in different companies cannot use animals, so we can make these models to test drugs, and we have done this with a few companies before. We can make swimming robots and mimicking nature. This is not from us. This is with cardiomyocytes, similar to a jellyfish, but cells can also contract and induce motion of components. But you can also combine, we have seen also catheters today, medical devices with muscles and cells that can contract and make valves and move fluids, or bend catheters like we have in this consortium, which is called BioMelt. Okay, so how can we build a multicellular system that is based on skeletal muscle tissue? So the technology we use, and Maria and others have been using for a few years in our lab, is the same picture as we saw in the previous talk, the Incredible Plus, right? We can use bioprinting. You can use a gel here, a composite of C2C12, myoblast, fibrinogen, right, and so on. And I mean, this was the initial one, but we have changed a lot, and we have a paper under review now with a cocktail, phase diagrams of depending what you want to have, which is the best cocktail for you. But you can make almost any shape. You can develop these muscles, and they are very functional. So the fancy thing about this is more on the, let's say, at the cellular level. So the shapes are very, very trivial. But what happens is that by the shear force, we've seen that the cells are aligned. And then this is basically very important for the cell function and the contractibility, as you can see here. So how do our muscles work? So the neurons will send an electrical signal and will respond. So we do exactly the same. We put some electrodes, very crappy one, like old-fashioned classic carbon there, but they are the best. I can tell you, like, we had a lot of discussion how to change and improve, and this is good enough. And by changing the frequency, you will see how they change the contractibility. Second aspect, I don't know if you have many injuries, you have gone to physiotherapy, or you have some electrical stimulation at home. I do, right? And in the lab, we have seen different things like that you can actually train them. By keep this electrical stimulation over 2 hours of time, you can see here, we've seen the force increase like 3 to 4 times. Again, how we measure that? By this simple model of the pillar. So we have 2 pillars, we know the Young modulus, we make the ring around, and by measuring the bending of this pillar, right, we can measure the force of that. We have used this, again, to age tissues, right, to print human cells and then make different phases and then recover the force and elasticity and different aspects of the cell. But we like things moving, and today is about swimming, so I think I think I still have some more time. I'm going too fast, but it's almost there. So we used these muscles to have something will move under the water. Again, we use the same printing technologies to print actually not the cells, but to print the skeleton. So Maria will tell you about the skeleton, why, and so on. But we made a mold. We took the ring of cells, we put into the skeleton. And remember, I was talking to you about this asymmetry, Janus, non-Janus particle, the same we'll need here. Okay, we need an asymmetry. So if you make a mold, a scaffold that with the muscle you will contract and expand, symmetrically, it won't go anywhere. That's very obvious. But if you just make with just a very small tip there, will give you a small difference in stiffness, and this difference in stiffness will make that whenever this is contracting and expanding, it will go in one direction and swimming. And you will see right now. So this is a tracking trajectory of an asymmetric robot. This is a symmetric robot, which does not go too far, by the way. Okay, so now we have something very simple, full of multicellular systems and hydrogels that are functional. They can contract, and also actually they can be self-training and get stronger and stronger over time. Again, the same way as before, we could control the contraction. We can do it here with the swimming. So 1 earth, and then 2 earths, and 5 earths. And by the way, I don't know if you will guess what will be the highest speed if you have higher stimulation. Is a higher speed? The answer is no, because after 4 to 10 hertz, so we get contractions, we get these cramps, like las rampas in español, right? So the muscle has contracted and then they don't go anywhere, and so you need to know the right parameters here. I told you about Purcell before, right, at the nanoscale. But now I'm going to tell you about Purcell at the milliscale or mesoscale. So we have seen actually that there is no correlation between the impulse, right, and the displacement. So actually there starts to be some inertia at this point. So when there was contraction, then after some hundreds of milliseconds, then is when the displacement starts to happen. So we are going into that larger regime still with a couple of zeros. Okay, so in the last 3 minutes, I will make Richard happy now, finally, right? This is just published again, like when a couple of, well, it's now 1 month ago, where this is a collaboration with Calgary and also with Maria here. So they have these sensors, and now I told you like we can use pillars to sense the force. So but what if we put this structure on a flexible sensor that by whenever it's contracting, it can be bending and then have a very nicely developed device that can be eventually portable as well. And portable to underwater, maybe. Oh, let me go, sorry, I went to the back quickly. I pressed the wrong button. Sorry, Richard, you see? It's bad luck, right? Here. Okay, so you can put it underwater. You cannot swim underwater, but this is the control, how it's bending. I don't know if the videos will be exactly now. And one nice idea that the guys had in the lab is to start stimulating or relaxing that, right? So we stimulate from the side with the electrodes still, but we sense, so how a contraction, so you put a stimulant that we will stick it to caffeine, please. So just with caffeine, it's enough to sense these peaks of contraction, and actually it's not synchronous, so it's like kind of spontaneous contraction, so it like accelerates very much, like today in the morning I was also very accelerated. I had to go outside because of the caffeine, right? But here you can also use relaxant, again, relaxant, right? And you can see how over time the force is decreasing, and also these peaks of force are decreasing over time. Okay, so I think this has a lot of potential. We just stop it here. We're going to continue with the collaboration to include more flexible electronics into different shapes. Can we bioengineer more real muscle? Because what you've seen is probably not too realistic. So that's what Florencia in my lab is planning to do the next couple of years to mimic all these type of structures. For that, you can do some digitally defined paths. And from here, she has had very nice code control from this university, which I cannot pronounce the complete name. So, but Okay. So reproducing this shape is, doesn't ensure that you can have something functional. So you can go towards these keywords of morphogenesis, maturation, and you need to do this by tethering them, anchoring them to some structure, and these are from the literature, some statements that people have done it. So that's what we actually want to do. So this is the aim of the work, and again, using the same simple printer, we can do all these very complicated structures and then embed it, and that's what we are having in the lab at the moment. Okay, so we have a muscle like a biceps here could be. And the next thing, again, I promised you about the integration. So we just got this project from the Barcelona Institute for Science and Technology to collaborate with ICN2, really top in electronics. And now Maria was also asking today, like, can you stimulate like locally or on demand? So we are not going to stimulate all the whole muscle, but we can use this small electrode and have a local contraction. Oh yeah, good. Fancy video, right? Well, I hope not everything is in green. No, it's worse, it's in black, right? Okay, just see these two posts. This is local, like a standard graphite electrodes that we're having stimulation everywhere. And the tetanic contraction means what I just told you before. Now, this is not working. This is not working, so let's go to the other one. Tetanic contraction is creating these cramps, right? Like when you don't leave the muscle and it's contracting, and you see the rest of the muscle keeps beating at the normal frequency, but we can stimulate that. And we are doing this for repairing damage, bone healing, and reactivation of some damaged tissues. Okay, so just to wrap up, I hope I could convince you that you can make autonomous, because we don't need to do anything. You've seen, we don't use any external stimuli. We use in situ fuel, chemistry which is in the water, to generate this motion. At the nanoscale, again, with these swarms that we've seen already, and also going in the larger scale with the soft robots using biohybrid and skeletons. So, yeah, I hope that I could also tell you a little bit about this, that this technological revolution is not that far anymore. We can shrink human beings, we can make submarines, we can put them into mice. Hopefully in 2-3 years, if we still have the funding, we can go in vivo and we can do sensing, repair, and all the things that these guys and all the collaborators have been doing over the last years, and this is just the current team from a few weeks ago. Thanks for the funding and you for your attention.
Thank you very much, Samuel, for a beautiful talk. Do you have questions from the audience?
Hi, Samuel. Thank you very much for the really nice, inspiring talk. So, regarding the last example you were showing, that you're applying the electrode to generate the mechanical contraction,
yes.
Does it also work in the other way around? I mean, if you are able to imagine we have a kind of magnetorological elastomer or something like that you can activate locally the contraction there,
yeah.
You get also the electric conduction propagating through the whole system and getting the contraction?
Well, that depends on your system, right? These are triboelectric sensors, so I think one of the ideas is to recover the energy from there. If we include nanoparticles inside the tissue, maybe you can extract some information or some energy from there, and that will be more on your side on the materials, right? So in our case, we are using for stimulation, we are using it for sensing, right? And with the triboelectrics, the plan is to get it both, but we are not using the magnetic. I mean, I think with Salvador a few years ago, right? There was this plan of magnetoelectric stimulations. Yeah.
Yeah, because I think it will be nice if you are doing mechanically, producing the electrophysiological thing and propagating, and then you could have,
and then supply the whole. Energy circular economy there, like also.
Yes.
Yeah.
Thank you.
Yeah. Great. There will be some problems there, right? On the we're talking to the lines, cytotoxicity, like dispersion there in the muscle, right? Like printability that we have under review. Some of the paper, right? Mm-hmm.
And to get good transduction at every cycle, at least at every step, I guess. Yeah. Do we have any more questions? If not, I'll make one. I think, because I'm a bit familiar with your words, so I think I kind of know the answer, but considering the audience, right, because there's folks here that have a strong background in robotics and controls, right? So typically when, controls is very important for a robot system, so you can control the direction, pre-program trajectories, right? So how do you integrate control in your nanorobots, right? Because you're using mostly chemistry for propulsion, right? Could you elaborate a bit on that?
Yeah, for a few years I was a bit hesitant on jumping until the others field, right? But now you see that the future is completely hybrid as well, right? People using magnetic control, they're using enzyme for degradation of mucus, right? So you see light and chemistry. So that's actually what we have in the lab. So we have a sub-team of light therapies. So you see light to activate this and to control. We used to have another person expert on magnetic control, and then you can have a core of this particle can be magnetic, and then you can give more guidance. So we have a couple of papers on that as well, on the guidance of this collective motion if you need, right? But again, with the chemistry, what I really like, and I've been struggling for 10 years, and now we really have an understanding, because I want to publish something like we are very sure about, and it's chemotaxis. So we know that there's some chemotaxis, so chemical gradients. But again, this is microfluidics, and then there are many factors affecting there. That's why this paper about these convecting flows is very important for the community.
You have a closed loop in a chemical system, I guess.
Then we used to have closed loop control as well with imaging and magnetic control. One thing for more control on the robotics, I think will be nice to put in one of these capsules, right, a large amount of these nanobots embedded there, and then the whole submarine will be bringing them near the area of interest and then deploy there and make the chemical action, right? Because, I mean, we need to be really realistic and honest, right? Like this works at the small scale. So the larger scale, you hear before, right? Like Stefan, like talking about like how many thousands of kilometers this can navigate, right? So you can put this into one of these instrumented robots and then deploy them there.
Yeah, great, thank you. No, I think this also illustrates there's another question?
Yeah.
Oh yeah, please, Fabrizio. Yeah, the different length scales and time scales also, right? Because at the end of the day,
pros and cons of
you want the right tool for the right job as well, right? So, thank you.
Thank you.
Fascinating talk.
Thank you.
Sorry for the silly question, but I think you have a look at really these types of systems are really within a sort of a human body environment, as a sort of a context. So there is a very restricted temperature and also some very specific constraints into the sort of the chemistry. Any chance that you have a look at how these kind of systems really could work when you start to be slightly outside really the sort of the normal body functioning or the normal illness body functioning?
No, it's not silly, of course. Like we are constrained into the human body because the main application we want to do, right? And you will hear later as well, like using different catalysis or catalytic materials, they are everywhere. They are not confined to 37 degrees and physiological media, right? I started with the platinum. The platinum, actually, one of the problems was that we could not use in the human body, but they're like functional for many hours outside, right? And we had another story with MOF, metallic organic framework, that can resist very high temperature with hard conditions. So that was another side effect, like a side project on how far can we go from that. So playing with the chemistry, but also playing with the materials, you can fine-tune a little bit, depends on the demands, on the applications. Yes. Yeah.
Thank you.
Yeah, you're welcome.
Great, thank you. So please, let's join me on giving him another round of applause.
Okay.